Okay, that brings us to chemical weathering. With chemical weathering, the minerals in the rocks are altered into something else. They break down, they decompose. Minerals can either be added, the minerals that are there can be altered, or they can be removed through chemical reactions. And minerals will react differently to chemical weathering. Quartz, for example, is very resistant. You know this because it forms at cooler temperatures and has that very complex crystalline structure. So it barely gets affected. When it does break down, it breaks down into smaller sand-sized pieces of quartz, and most beaches of the world are made of quartz. The sand there is quartz. So it doesn't disappear for good. Feldspar, another component in one of our favorite rocks, granite, can be easily altered, and chemical weathering is going to be strongest in warm, humid areas. Again, we have, what do you do in chemistry when you want to speed up reaction? You add heat, right, or some type of fluid. So chemical weathering is going to be more prominent in warm, humid areas of the earth. So there are several types of chemical weathering. There's oxidation, there's dissolution, and there's hydrolysis. So we're going to get into a little bit of chemistry here. Rocks decompose mainly because of two major substances that are in our atmosphere, oxygen and carbon dioxide. And oxygen, really on its own, it doesn't do too much, but when oxygen is dissolved in water, it's aerated, it can go to town. Carbon dioxide in our atmosphere reacts with water, rain, as it falls through the atmosphere. CO2 is one of the components in our atmosphere. So that water can react with CO2 to give us carbonic acid. Carbonic acid is H2CO3 right here. Where's my pen? Got to get it over here. Water plus CO2 gives us carbonic acid. It's a fairly weak acid, but rainfall, average pH of rainfall is about 5.4. Well, if you know anything about the pH scale, you know that 7 is neutral, and we go up to 14 up here, and anything higher than a 7 is alkali, and anything lower than a 7 is acidic. Acid, basic, same thing, alkaline. So 5.4, that's less than 7, isn't it? So normal rainfall is slightly acidic. And when that slightly acidic water percolates into the ground and comes in contact with grasses and organic material, it can become even more acidic. And then look out what happens when that water reacts with carbonate rocks. So carbonic acid can speed up weathering. Oxidation happens when minerals in rocks react with oxygen either in the air or water. And a really good example of that is rust. Fe plus oxygen gives us FeO2, iron oxide. Anytime you see red rocks or red soil or yellow rocks or yellow soil, it's because the iron in those has been oxidized. Mars is the red planet. Why? Because of rust. Oxidation has taken place. And here's a good example of that. Red Rocks in Colorado. Maybe some of you have heard of Red Rocks. It's an amphitheater where a lot of music can be heard. So these rocks, these were flat-lying rocks at one time, flat-lying sandstones. And then the Rocky Mountains rose, and as the Rocky Mountains rose under them, the rocks became tilted like this. If you've been to Morrison, Colorado, outside of Denver, you see these big honking rocks tilted up like that. They're called flat irons. because that's what they look like, I guess, to the people, pioneers coming out. But those were carved into to form this stage, or form seating here, and down here's the stage. But look at them. Beautiful, beautiful slabs of beautiful red sandstone. Here's some layers. Good clue, if you see layers like that, you're dealing with sedimentary rocks 9 times out of 10. And here's the seating. See, set up here, the stage is down here, and Denver is off in the distance, so at night you can see the lights of Denver. Dissolution takes place when minerals in the rock dissolve. An example would be salt dissolving in water, very easy to do. And then we already talked about when rain falls through the atmosphere, it dissolves some CO2 and we get that weak carbonic acid. And that acid then makes it more easy for other minerals to dissolve, like sodium, potassium, carbon, our sulfate minerals. Like, anybody remember what a sulfate is? Gypsum. So gypsum is a mineral, but gypsum is also a rock. And here's our formula, H2O plus CO2 gives us H2CO3. Then that can be broken down into a hydrogen ion and a carbonate. When we're talking about dissolution, limestone is a good rock to use as an example because it's composed mainly, almost totally, of calcium carbonate, calcite. When acid, and you know this from our HCl experiment, hopefully if y'all have a lab, you've maybe not done this yourself, but hopefully seen it done. When we put dilute acid on a carbonate, what does it do? It fizzes away. It begins to fizz away, right? You see a little puff of smoke. CO2 is being released into the atmosphere. Well, when that acid comes in contact with rocks, with limestone rocks, it's going to start dissolving them away. So caves are nothing more than holes in the limestone that chemical weathering, that dissolution has destroyed. Not totally destroyed. Matter cannot be created or destroyed, right? So if you have been to Tennessee or Kentucky and maybe you've driven the highways and byways in those areas, you see that the road cuts look like, in some places, look like this, like somebody has been out there, a master mason has been out there and laid these blocks. Well, the master mason in this case is Mother Nature. This is the tendency, again, these jointing patterns that we talked about before. The tendency of let me figure out how to say this. The weak areas in calcite or in limestone tend to be in these nice linear shapes. Let's just emphasize that for a minute. So those are the weak areas. So where's the water going to go? The water is going to head into those weak areas. And my goodness, doesn't it just know that it has hit the jackpot here, because it can start dissolving all this calcite away. So we're talking about groundwater, maybe water that's coming in from the surface, maybe it's an aquifer here, and these void spaces that we find would be caves. Caves or caverns. Well, the water continues to move. You know, we have huge formations of limestone. So the water can continue to move, and when it moves, it's getting more and more saturated with calcium, with calcite. So it might come into another area and the temperature might be a little bit different, or maybe it's just holding so much calcite that it can't dissolve anymore. What do you think will happen? That water begins to drip from the roof, and with every drip, we get a little calcite formation that will be forming. The water hits the floor, and with every drop that hits the floor, we have a calcite formation that grows up from the floor. And you all know what these things are called. Hopefully you've all visited a cave at one particular time in your life. If it's hanging from the roof, it's called a stalactite. If it's growing up from the floor, it's called a stalagmite. I always remember that because of T, top, and the G, ground, growing up from the ground. If they grow together, it forms a column. And there are so many cool features. Just the imagination goes wild when you think about the different features that you've ever seen in a cave. Some of them make no sense at all, like those that grow out vertically and then do a twisty kind of thing. And you wonder how in the world that just defies gravity. But it happens. Then you get the ones that are called soda straws that, again, when you think of the water coming down, drop of water has a hole in it, doesn't it? So the calcite is precipitating where we have the water, and then the hole, there's nothing. So it forms these straw-like formations. So here's Mammoth Cave in Kentucky. Kentucky is a big limestone state. And here is a stalagmite. Here's some stalactites. Don't see a column anywhere. That looks like it could be a column at some time in the past. These are just like drapery. In fact, I think that's the term for it when you have these sheets of calcite that have formed from water flowing down the side of the cave. It's a whole nother world underground. But unfortunately, that underground can reach up to bite us sometimes when we get sinkholes that form. And the sinkholes form because, look at all of these little rectilinear features here, because the roof of the cave continues to grow upward, 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 until there's nothing overhanging it, and it just collapses, and we get a sinkhole. Sometimes the sinkholes are filled with water if the bottom of the sinkhole intersects the groundwater table. Sometimes they're not. But, you know, maybe hobbits live down here, just a whole different world. And unfortunately, that subterranean world can sometimes ruin our surface world. This is in Florida. Florida is another state. It's totally made of limestone. So they get sinkholes there all the time. This one has collapsed and taken out the backs of these homes. Here's another sinkhole. And all of these are sinkholes. So you've got this nice little homestead right here. Do they even realize that there are void spaces underneath them here? That's why most states have a karst educator. An area underlain by limestone like this is called a karst area, from this area in Slovenia called Kurs, with caves and sinkholes and waterfalls. So usually a state geological survey will have a karst educator to go out and talk to people about what they can do to keep their groundwater safe, what they can do to keep their animals safe, and, you know, people living there safe. Sometimes there's nothing. So when rain reacts with carbonic acid, that is a weak acid. But acid rain is stronger. There's a stronger acid rain. We don't normally call rainfall acid rain. However, we might go to other parts of the country, other places in the world, and they really have acid rain. And that is usually from a reaction with things that have been put into the air by us. So I love this word right here, anthropogenic. That is us. Anthropogenic is human origin. So these sulfur dioxides and nitrogen gases go into the air from cars, from factories, from power plants, and it makes the acid rain more concentrated. The weathering gets accelerated in ways that are totally not beneficial. In some regions of the world, rain has a pH of 3. That's like battery acid. And you can imagine what the impacts are going to be on aquatic life, on plants, forests, and also monuments made of marble or limestone or other susceptible rocks. You see a lot of places like Athens and Paris, London, they're constantly doing maintenance on some of their buildings and important monuments to keep them from, looking like this. This is Cleopatra's Needle, this monument right here and here. This is Cleopatra's Needle. Cleopatra's Needle, there were about 4 of them, I think, and when Napoleon was in Egypt with his army, they excavated these things. One is in Egypt, there's one in Paris, there's one in London, and Egypt made a gift of one of them to New York City. Well, this is the one in Egypt. Egypt is a dry climate, right? This is the one after 100 years, and this has been here for over 5,000 years in Egypt. This is New York City after about 100 years. So that's acid rain that has caused that monument to be degraded the way it is. And here you see the poor angel that's been blackened and from pollution. And then this gargoyle, what happened to its legs? Well, they've weathered away. Then the third type of chemical reaction is hydrolysis. Hydrolysis is where water reacts with a mineral to form a new mineral that has water as part of its crystalline structure. Granite, fairly resistant to weathering, especially in arid climates, but it will break down over time because acid rain goes after the feldspar crystals. Those would be the pinky colored crystals, part of the matrix of the rock. So the quartz, hardly, okay, nothing much happens to it. But the feldspar breaks down into clay. So this is the feldspar, the 2KAl potassium aluminum silicate here, plus hydrogen ions and water will break that down into aluminum silicate oxide with water. That's the OH part here, and some potassium ions and some silica. These two will get into groundwater and go somewhere else. This is a clay. If I can get my pen to work properly here. This right here is kaolinite. I think I've talked about kaolinite before. Kaolinite is a really pure white clay that is used in pottery. So we have this fairly resistant granite that over time will break apart because the structure, the internal structure, when you think about all these crystals in here, the quartz crystals, the feldspar, the plagioclase, the orthoclase, hornblende, biotite, and let's say these are the feldspars. Well, what happens when we take away part of that structure? That is going to dampen the integrity of the whole crystalline structure. So this is rotten granite right here, and this is what has happened. The kaolinite has been subjected to hydrolysis. Here's kaolinite, right there, nice, pure, powdery. So it's a type of clay. And then here's a formation of kaolinite. So chemical weathering will break silicates down into these elements: sodium, calcium, potassium, and magnesium, and plants use those elements then to grow. You know, when we have fertilizer, what do? NPK, nitrogen, phosphorus, potassium. Iron, again, will react with oxygen to produce reddish or yellowish color that we see in soil. And aluminum and silica and oxygen, along with water, will produce the clay minerals. Two types of weathering are better than one. Physical weathering can expose more surface area, and that in turn is exposed to air or water. And chemical weathering will dissolve minerals that make the rock more susceptible to breaking down, like that granite that we just looked at, the rotten granite that we looked at. Both types happen faster at the edges of rocks, and even more so at the corners of rocks. So there's this tendency of these angular pieces to become more rounded over time. And again, it just makes sense. Not all rocks are going to weather at the same rate because they're composed of different minerals that weather differently. And we call that differential weathering. And a lot of the landforms that we see out and about, they're these spectacular features just because the minerals that they're composed of weathered at different rates, like the little feature that I showed you at the beginning in Utah.